It's no secret that as things get hotter, they expand. About 1,000 years ago, or so I'm told, I wasn't there, someone asked the question, is the reverse also true? If something expands for reasons other than temperature, would it get colder? And there you have the basic principle of Rankine cycle refrigeration. If you compress the gas, put a large amount of it into a small space, pressure increases and the gas gives off heat. If you then put a small amount of that pressurized gas into a big space, it expands and takes in heat. If you compress a gas enough, it turns into a liquid. Take the pressure off and it turns back into a gas. If you compress the gas in a sealed space which is permeable to heat, say a metal tube, the tube gets hot and then the heat goes off into the air. When you take the pressure off, the gas expands again and it takes in heat from the tubes surrounding it. They get cold. If you apply enough pressure, the gas becomes a liquid, and that's about as far as you can readily compress it. Just before it becomes a liquid, it becomes a vapor, which is not quite a gas nor a liquid, and that's what refrigeration units use, a vapor. The compressor compresses vapor into a hotter vapor, which cools to a liquid under high pressure as it travels down the tubes. It encounters a very small hole at the cooler end of the tube and gets squirted through, thus reducing the pressure on the hot liquid so it expands and after a while becomes a vapor again, but at a lower temperature and pressure. And so it takes in heat. Taking in heat is refrigeration. So what is a refrigerant? There are many types of refrigerant gases known by many names such as R22, R11, R410A, all sometimes and inaccurately called Freon, and they all share a common property. That being, at a pressure which is not too far above atmospheric, they are transformed into a vapor. Vapor is a state which is very near liquefaction. Compress a vapor a little more and it becomes a liquid. So, what's compression? Refrigerant gases are readily condensable, which means that it is easy to get the molecules to squish together into a smaller space. As they get squashed, the molecules are inhibited from moving as is their nature to do, and in order to move less, they have to give off heat. Therefore, temperature and pressure vary directly with each other. The temperature of the refrigerant increases as it is forced into a smaller space. The higher the pressure, the more heat they give off. In this rather crude illustration, we see the basic refrigeration cycle. The compressor is that black box at the top labeled compressor, and the colored lines represent metal tubes that the compressed refrigerant is moving through. The white arrows indicate the direction of flow. In practice, the tubes would be a lot longer than they are shown here and most often bent into a series of coils. The compressor squashes, condenses, the refrigerant vapor, which would turn into a liquid immediately except that there is no place for the heat that it needs to get rid of to go. So it remains a vapor coming out of the compressor. The excess of heat flows out through the walls of the tube and gets absorbed into the air. That causes the vapor to liquefy. The point at which it does so, the refrigeration guys call the saturation point. That is the definition of saturation. The temperature at which the refrigerant vapor turns to a liquid, from a vapor, or from a vapor to a liquid at a given pressure. This also defines our two other words of question. Superheat is anything above the saturation temperature, and subcool is anything below the saturation temperature. Remember that the saturation temperature depends on the pressure. Now back to the illustration. The compressor compresses the vapor. That's an important point about the compressor itself. If the refrigerant gets to the compressor in a liquid state, that's called slugging, and it is really hard on the compressor. The tube leading out of the compressor to the hot side is always a vapor, and the tube leading into the compressor is always supposed to be a vapor. If that doesn't happen, the whole thing's broken. As the refrigerant flows down the tube on the hot, red side, it is always giving off heat. Eventually, it gives off enough heat through the walls of the tubes that it condenses into a liquid. This is what is called the saturation point. Before the liquid gets to the midpoint in the cycle, it encounters a metering device. The metering device is a flow restrictor. It has a hole in it that only allows a little bit of the refrigerant liquid through. It can be a thermal expansion valve, TEV or TXV, what is called a piston, or a capillary tube, a very narrow piece of tubing, and they all do the same thing in different ways. That is, they reduce the pressure of the liquid refrigerant before it gets to the evaporator coil. The condenser coil is where the refrigerant condenses into a liquid, and the evaporator coil on the other side of the metering device, flow restrictor, is where the refrigerant evaporates back to a vapor. Once past the metering device, the liquid refrigerant is at a much lower pressure and is flowing into a usually larger tube, so it expands. This process of expansion takes in heat. The liquid flows back towards the compressor until it once again reaches the saturation point and expands back into a vapor. That is the refrigeration cycle at its most basic. Reviewing, the saturation point is the area of the tubes where the refrigerant is transforming between liquid and vapor. Superheat is any temperature above the temperature of the saturation point, and subcooled is any temperature below the saturation point. Remember, there are two different saturation temperatures in the refrigeration cycle because there are two different pressures. Advancing the whole idea, if you place an insulated box around the condenser tubing, the box gets hot inside and you have an oven. If you place an insulated box around the evaporator tubes, you have a freezer. This picture represents a little more practical version of the refrigeration cycle. On the left are colored lines representing the condenser coils, the area of the tubing where the heat is given off. The black line around the coils represents an insulated box. If you were to put such a box around the condenser coils, the inside of the box would get hot until you had an oven. At the bottom of the picture, the gray thin line labeled metering device represents the metering device. That is the thin bore tube that reduces the refrigerant pressure and deposits it at the evaporator side of the machine. The thick black line around the blue evaporator coils is again an insulated box. On this side, the tubes are taking in heat, so you have a freezer. The white color in the tube represents the vapor state of the refrigerant. The red, the hot refrigerant, and the bluish, the cooler. The solid green represents the saturation point. Again, that is the point in the process where the liquid-vapor or vapor-liquid transition is taking place. Although it is represented here as being of a definite length and location, that is not correct. Saturation occurs wherever it darn well feels like. An important peculiarity about the saturation point is that the actual temperature stays fairly constant. Just as water on the boil at sea level is always 212 degrees Fahrenheit until it turns into steam, much the same principle is at work here. While the refrigerant is losing or gaining heat through the process, it is not sensible heat, because the temperature remains the same. The HVAC guys call this latent heat. My high school chemistry book called it the heat of vaporization.